next paper is going to be by Professor Darrin Byrd from Texas A&M University, talking on the identification of the various modes of carboxylate binding to metal centers by infrared spectroscopy.
Well, it's indeed a real pleasure to have been included by the organizers of this symposium to participate in a symposium honoring Bob Ishins. I probably owe some of you a little bit of an explanation as to why someone coming from an area that's not really very closely related to what Bob has done in the past would be invited to participate. Well, in 1967, when I was finishing up my PhD thesis with Ted Brown in Illinois on infrared intensities of metal carbonyls in solution, I started applying for my first job. And the first place I wrote was the Texaco Research Center in Vegan. And to my surprise, right away I got back a letter inviting me to come out and visit them. And I had heard that there was some infrared work going on there, but being a naive graduate student, I didn't know what was going on in Texaco. So I quickly went to the library and looked up the most recent text dealing with this subject, and there was this book by Professor Little. And I didn't have to read very far, that is in the preface of the book. Right away, I was informed that some of the greatest advancements in the area had been done by Bob Ishins. And indeed, I did go for the interview and ultimately got to work with Bob, had a very educational and informative 9 months with Bob, and appreciated that quite a bit before going into an academic job. What I'd like to talk with you a bit about today, and I've sort of, an alternate title to my talk might be an organometallic chemist's guide to surface chemistry. And you might recognize this title. I've sort of rearranged a book in this area entitled A Surface Scientist's Guide to Organometallic Chemistry. But what I want to talk about are some very well characterized metal carboxylates in which we know the solid state structure in great detail, and we know the solution in infrared spectra, both the solution on the solid state infrared spectra is very well assigned. And hopefully that information then can be transferred to carboxylate species at metal surfaces. Well, if we look at the way a carboxylate ligand might bind to a transition metal, it might bind in a monodentate fashion, in which only one of the oxygens is bound to the metal, or it might be chelating or bidentate, where both oxygens are bound to one metal, or it might be bridging, where two metal centers are bridged by the carboxylate. Now, our interest is in carboxylates, and one might include in this discussion formates, has involved the reaction of CO2 with metal alkyls or metal alryls and metal hydrides. And these reactions, of course, could occur on metal surfaces as well. There's one other surface species that has been mentioned, and that's one in which a carboxylate can act as a bridging ligand between two metal centers via one of its oxygen atoms. And I have never seen a carboxylate bound in this manner in homogeneous or organometallic chemistry. However, I was reminded by one of my students, when R is an OH group, it is, when it's a bicarbonate, we do indeed see a structure of that type. And I show you here, this is a dicopper species which has two phosphines, two triphenyl phosphines. I've left the phenyl groups off for clarity. And the two coppers are bridged by two bicarbonate groups, where one of the oxygens serves as a bridge to two copper centers, and then the bicarbonates are hydrogen bonded to one another. So there is some evidence for those type structures in isolated, well-characterized molecules. Well, the way you would use infrared spectroscopy to assign the structure of carboxylates bound to various metal centers is to use the symmetric and asymmetric vibrations, and in particular of the CO2 species, and in particular look at the difference between the asymmetric and the symmetric CO2 stretch. For example, in an ionic acetate species, the difference is on the order of 164 reciprocal centimeters. Now, when the carboxylate binds in a unidentate fashion, what we generally see is that delta is much greater than this ionic value. Generally, it's above 200 wave numbers, but it's of course dependent upon what the delta is for the particular anion, because that can vary all over the place depending upon the carboxylate in question. Secondly, when you're looking at a chelating complex, delta is significantly less than the ionic value. And as a general rule, that's the case, but what I'm going to show you is that you have to be careful in these last two regions. And the bridging complexes, generally delta is greater than what you would see in a chelating complex and closer to the ionic value. So these two areas are a little bit fuzzy, but I'll try to clarify it a bit. So if we look at again, a well-characterized copper species, and this is a copper with adipic acid, where both carboxylates now are bound to copper centers which have two phosphines. This molecule is carbon-13 labeled at both CO2 sites, 100% or 99%. So we've used it to absolutely nail down the frequencies for the carboxylate. And here, what you see on the bottom, these two starred peaks are the asymmetric and symmetric stretches for the carboxylate bound to copper in a chelating fashion. The difference in frequency between asymmetric and symmetric, that is delta, is about 141. So it's getting fairly close to that 164 for an acetate, because an adipate has a similar ionic value. And similarly, if you now make this with carbon-13, you see those bands shift. So one can unambiguously assign the symmetric and asymmetric with carbon-13 labeling studies. On the other hand, if one now goes to copper-1 acetate, I should have pointed out all those copper complexes are copper-1 complexes. If we go to copper-1 acetate, which is basically a planar dimer, and there's weaker copper-oxygen interactions between dimers, that is, there's an extended structure. If one reacts this molecule with one equivalent of DPPE, which is the bis-phosphenoethane molecule, bis-diphenylphosphenoethane, this chelating phosphine. If you reacted 1-to-1, you get one complex. If you reacted 2-to-1, you get another complex. And one can identify those complexes, that is, tentatively, by infrared spectroscopy. What you see for the DPPE 1-to-1 is that the difference between the asymmetric and symmetric is 167. So by what I told you in the beginning opening slide was that this then should be a bridging carboxylate. When we use DPPE 2-to-1, that difference is 224. So what we expect then for the 2-to-1 is that we have a monodentate carboxylate. That molecule, this latter molecule, we've not been able to crystallographically identify, but we have a structure of a chloride, and we assume it's something like this. On the other hand, the molecule prepared from 1-to-1, that is, a copper dimer acetate with one equivalent of bisphosphine, what one sees is that the phosphine indeed is bridging and the carboxylate is bridging the two copper centers. In other words, accounting for that 167 splitting, something bigger than what one saw for a chelating system of the acetate. And the acetates then just bend back out of the plane to accommodate the phosphine. So there's very little change in structure of that species. And you see also the extended structure involves this added copper-oxygen weaker interaction, as you saw in the parent molecule. Now, if we make a series of bidentate carboxylates bound to copper, all containing bisphosphines, and look at the asymmetric and symmetric stretch, I should tell you straight off, which I'll show you in a second, is that all these compounds are bidentate from X-ray crystallography. And if we look at the asymmetric to symmetric, that difference for the acetate is 143, which is below the ionic value, so you would anticipate that it's bidentate prior to doing the structure. And in fact, for all the others, the ionic values are listed here, and the difference between the asymmetric and symmetric in both the solid state and solution are listed here. And what one sees is they're all a little bit higher, or very close to the ionic value, somewhat lower than the ionic value, but quite close to it. Yet I've told you that they're all bidentate, and this is where the fuzzy region comes in. Let me just show you one of those compounds. There's the acetate, and we have structures of all of them. I'm not going to show you all of them because I'll summarize that on this view graph. If you look at what happens is copper 1 is a D10 metal, and it really doesn't care whether it has 4 ligands or 3. And so what happens is the carboxylate, even though it's bidentate, it's asymmetrically bound. That is, one of the carbon-oxygen bonds is, one of the copper-oxygen bonds is longer than the other one. And so it's moving somewhere between a bidentate going toward a monodentate. And when you do that, the separation in asymmetric and symmetric gets bigger. And what I've done here is just summarize. If you look at the carboxylate bound in a bidentate fashion to copper 1, then these parameters